that this Planck constant, the value doesn't depend on the choice of the Planck constant. So in particular, if you send this Planck constant to be 0, and this integral will be localized to some constant maps, which is an integration like some expressions, local expressions. And on the other hand, you can show like, well, the left-hand side basically is the physics way to express what is the index, analytic index. And the right-hand side becomes a local expression. It becomes a topological index. And this is the physics derivation of Atiyah-Singer index theorem. Now, although this actually, the physics idea is sort of, it's very clear, and not only providing an understanding of this index theorem, but actually also like illustrate some new ideas about new index I will explain in this talk. So there's another phase of this index theorem, which is called algebraic index theorem. It's the following, like I'm gonna state the simplest version. So given a deformation quantized algebra, like this is M is a symplectic manifold, where the function ring is a Poisson algebra, then you can look at this deformation quantization. This is a star product. Then you can show there exists a unique linear map, a trace map, like unique up to a normalization condition and satisfying the trace property. And if you normalize it carefully, you got a trace map. Then if you compute the trace 1, in physics, it's related to the partition function. Then you find this expression, like integrations of some forms, like this is a roof genus. And this form relates the moduli of the choice of the deformation quantization. And this is the simplest version of so-called algebraic index theorem, which was first formulated by Balasov and Nassigan as the algebraic analog of Atiyah-Singer index theorem. And actually later Nassigan, they show the general form of this algebraic index implies this Atiyah-Singer index. So this is a very strong statement. Now, I mentioned like this physics idea about the index actually illustrate a new idea, like which has been a very important problem in geometry and topology. It's like this. So, for example, you can replace this circle by an elliptic curve. You can look at a two-dimensional quantum field theory. Then you can do the same thing. If you have supersymmetry, you have topological theory, you can rescale this parameter. Then intuitively, you can think about this mapping space from the torus to X as a mapping space from the circle to the loop space. Then this basically defines the quantum mechanics on the loop space. And this leads to Witten's proposal for the index of Dirac operators on loop space. And the rigorous construction of this operator, this index, is not done yet. It's still open. But in this talk, I will explain an algebraic theory of this one, which I call higher algebraic index theory. So this is one of the introduction. Now let me first explain how some notions of homological algebra in non-commutative geometry arise naturally in quantum field theory. And the first idea I want to explain is the following. Like, there's a classical theorem which is called Hochschild-Kosten-Rosenberg. I would like to explain the idea that this classical theorem can be viewed as a version of renormalization group flow. So once you realize this, this notion, then this will play an important role to generate index to higher dimensions. I will try to explain later. So let me first explain this Hochschild homology and this Hochschild-Kosten-Rosenberg type theorem. It's the following. Suppose I have an associative algebra. Then I can form this Hochschild chain complex where like the P strand is given by P+1's tensor of the algebra. Then you can write down a differential like this. So basically, you look at all the pairwise product, like A0, A1 minus A1, A2, etc. And the last one you multiply to the front. And it's alternating sum. So the picture is like this. I mean, suppose you put things on the circle, then you look at all the pairwise collision. And this picture will have a very physical meaning. I will explain in a minute. So you can check like this differential square is 0, so defines a chain complex, and the corresponding homology is called Hochschild homology. Now, this classical theorem of Hochschild-Kosten-Rosenberg says the following. Let's look at the simplest example, like the A is like a polynomial ring. Then this HKR theorem says like if you compute this Hochschild homology, you basically obtain the differential forms. And in particular, you can write down a rather explicit map interturning these two chain complexes from the Hochschild chain complex to forms by this most naive one. And this one tells that actually this Hochschild chain complex describes the analog of differential forms in non-commutative geometry. So that's why it becomes a very important notion in the quantum theory. And in this talk, I will describe a realization of this quantized map, and which is going to be related to the index theorem. So I would like to start with a very simple toy model, which motivates the construction. The toy model, which is called quantum mechanics, topological quantum mechanics. And there's a big machine behind this construction, which is called AKSZ construction. But to be simple, like here, the model is a rather naive one. So the space of field for this model, it's given by, look at this quantum mechanical system on the standard phase space. Then the space of field is given by 2n copies of differential forms on the circle. Then you can write down the action functional, which is the most naive one. It's the free theory, like PDX or XDP. Then this is free theory, and you can look at, you might ask like, well, this is free theory, what you can do? Actually, you can have interesting observable structure. And for example, if you take any function on the phase space, then you can define an observable like this. So you can write, you insert this field, and because this is like differential forms on the circle, you can decompose this one into 0 form and 1 form. And so this give rise to 2 types of observables. And if you are familiar with topological field theory, this is related by this so-called topological descent. Now, here's the idea. You do the following, which is the actually interesting construction. You put observables on the circle and compute their correlation function in the free theory, and then let them go, run over all the places, preserving the cyclic order. Then this gives rise to an interesting map. And actually, if you are familiar with like so-called BV quantization, this map can be viewed as a BV push forward to 0 modes. Then with this map, so you put all the local operators on the circle and let them run, and you find the following. This is one of the theorem. So this correlation map interturns the Hochschild chain complex of the canonical quantized algebra, which is the wire algebra. This chain complex to the forms, differential forms on the phase space, which interturns the Hochschild differential with this delta is called a BV operator in physics notation. Here in geometry, this is the lead derivative with respect to the Poisson biovector, and interturns the Kunis operator, B operator, with the Ram operator on the differential form. And in particular, this correlation map gives an explicit formula for the quantized HKR map. Now you can do a little bit more. You can glue this map on a symplectic manifold, and you can obtain a trace map on deformation quantized algebra, which is the famous Feigenfeld-Schottky formula. And then you can use this model. You can do some kind of formulate the BV localization formula, and use this one to prove this algebraic index theorem. This is like done in these 2 works. And they also can formulate this topological quantum mechanical model on symplectic orbifolds and obtain some orbifold index. So this is a motivating example. It's one-dimensional case, how you can obtain index from this quantum mechanical system. This is called algebraic index. Now, this Atiyah Singer type index is something we know pretty well. Now, I would like to extend this construction to 2-dimensional case. And this is related to the algebraic version of this like index for Dirac operators on the loop space. Now, here's the comparison. Like in the 1-dimensional case, everything is on the circle, 1-dimensional topology. So observables, when they collide, you have multiplication from the left or from the right. You have associative algebra. In the 2-dimensional case, I'm going to work with like chiral theory, which means that if you have 2 local operators on the Riemann surface, and when they collide, you have some operations which depend on the location holomorphically. So you can collide by rotating like 10 times, or you have Fourier modes. This leads to an algebraic relation, which is called operator product expansion. And then we discover this so-called vertex operator algebra. Now this is the algebra in 2 dimensions. This is a little bit different from the 1-dimensional case, where you just have algebra and the representation. Now here's a basic example. This is the only example I will explain in this talk. It's a beta-gamma BC system, which is a beta-gamma system is the higher analog of this wire algebra. And the BC system is the higher analog of Cliff algebra. So if you look at the generators, the field, beta-gamma bosonic field, and this, if you look at the OPE, you have the singular term 1 over Z minus W plus some regular terms. This is how it looks like. And the BC have the same structure, but the BC fermionic field is a little bit different. And then give rise to a higher algebra in the sense of a Bennington dream field. If you turn this one into a right D module on the Riemann surface, this is a very standard construction. So this is like play the role of like differential operators on the loop space, if you like. Now, then I have to understand what's the corresponding chain complex, which going to be related to the index. In the 1-dimensional case, you have this Hochschild chain complex. In the 2-dimensional case, it turns out that the natural complex is the higher chain complex. So in particular, I'm going to work with like elliptic curve. It relates to the so-called elliptic chiral homology. So like a long time ago, like 1994, like Yongshang Zhu, he studied the space of genus 1 conformal block, where now it's called like zeros elliptic chiral homology, and established this modular invariance for certain class of UA. This is a rather remarkable result, like for rational type and etc. And then Bennington dream field, they define this chiral homology for general algebraic curves using this Chevalier-Cassin complex. And this is a pretty categorical reconstruction and make it very abstract and difficult to compute. And recently, like Akram and Halouani, they actually find some explicit chain complex expressing the first few terms in this elliptic chiral homology. So you can play by hands to compute some examples. So I won't spend time to explain this, this construction, but naively, the idea is the following. It's very similar to the Hochschild differential, but in the Hochschild case, like you put things on the circle, you look at all the possible collisions. Like you think about this one as like a degeneration. Then on the Riemann surface, like say on the torus, you put the local operators on the Riemann surface. You have to remember it's a holomorphic structure. And then this chiral differential basically do something similar. You make pairwise collision and try to compute some residues and insertion. This is the idea about this map. And then you can make this operation categorical and in a direct sense and so on. So that's defines this chiral chain complex. Now, here's the theorem. So suppose let's work on the elliptic curve. And then you can in the same fashion as I explained in this topological quantum mechanical model, which explains this Atiyah-Singer index. Here, you basically work with the chiral chain complex, elliptic chiral chain complex. Okay, elliptic chiral chain complex. And you can look at, again, a similar correlation map, interturning this chain complex to a nice algebra. This is, again, a BV algebra. Interturning this chiral differential with a BV operator. And this is constructed as follows. So again, this looks like a correlation map. Then this A2 right-hand side is some finite dimensional algebra. It functions on the 0 modes. So this map actually, again, can be viewed as a BV push forward in the 2-dimensional case. Second, you can show this actually is a quasi-isomorphism. So remember, in the 1-dimensional case, you have a quasi-isomorphism, which is the Hochschild-Kosten-Rosenberg theorem. So this map is also a quasi-isomorphism. So you can view this one as the chiral analog of this quantum HKR. So this makes it very useful to do some calculations. Thirdly, this notion, I will write, this one is the local correlations, like between local operators, O1, O2, etc. And it can be constructed either using Feynman diagrams in the perturbative theory or using some conformal block in representation theory. Either one works. In this talk, I use this, in this work, I use these Feynman rules. But then you see like there's an integration here. This is the tricky part. You find if you compute local correlations in this two-dimensional conformal field theory, this guy actually is very singular. So for example, when Z1 approach Z2, you can produce the order like 1 over Z1 minus Z2 to the power 2024, for example. It could be very singular, and the naive integration gonna be divergent. Now, you have to design something to make sense of this integral. And this is the so-called regularized integral that I introduced with my colleague Jie Zhou, who is also a faculty here. Yeah, we call this one a geometric renormalization method for this two-dimensional chiral quantum field theory. And this one, this regularized integral has a few remarkable properties. I just mentioned a few later. And finally, if you do the trace map in a similar fashion that I mentioned, you compute the partition functions of the model, you'll find the Witten genus appears. And that's exactly what you expect for this, this index theorem on the loop space. So that's the, you see like this page basically can be viewed as the 2D analog of this 1D model, which is motivated by studying this Witten's proposal for this Dirac operator on the loop space. Now, we call this one elliptic chiral index. It's actually, the reason is because it's motivated by the work of Michael Douglas and Robert Digraph. They studied basically the partition function of so-called chiral deformation of conformal field theory. By deformed theory, by adding on some chiral Lagrangian density, L. So this chiral means like it only involves the holomorphic derivative. Then if you quantize the deformation, you quantize this theory on the elliptic curve, you can compute this partition function on the left-hand side. It's modular, but actually it will exhibit some kind of holomorphic anomaly. And it can be related to a very nice representation theoretical object, which is a Q trace on this chiral algebra, which is the right-hand side. And they are not exactly the same. There's a limit, like linking these two. Naively, the left-hand side, if you compute the left-hand side, you will find the so-called almost holomorphic modular form. It's modular, but if you have a mild Hobart dependence. On the right-hand side, it's gonna be holomorphic in tau. You see like Q is only a holomorphic in tau, but it's not modular, it's quasi-modular form. This is like a second, like Eisenstein series, E2 and E2 star. Then you can show this kind of the index. One of the reasons this kind of property holds actually can be explained in terms of this regularized integral I just mentioned. So for example, how this limit link these two, and this is the work in the same work. And then you can show like this one satisfy the expected holomorphic normal equation and also the contact equation like proposed by Douglas and Digraph. So this is one of the structure I want to mention. Great. So finally, I would like to explain the summary. Like in the one-dimensional quantum mechanical system, we are playing with this associative algebra and this Hochschild homology, and then you construct some correlations in this model, which intertwines the Hochschild with the BV, and then you can obtain this algebraic index. So the right-hand side is the stuff, the new stuff. This 2D chiral model, where you play with this kind of vertex operator algebra and this corresponding chiral homology. And then if you use this regularized integral to integrate the singular correlations, you end up with this chiral index. And in particular, you obtain this Witten genus in this model. And this is joint work with Zheng Pinggui. Now, I would like to explain the original motivation of this work. And actually, I say this application, but actually this is the original motivation for this work. We try to understand the so-called quantum B model. And, you know, this is a very famous work of Bachevsky, Tsakodi, Oguri-Vafa. They propose that this B model on Calabi-Yau can be formulated by a closed string field theory called Kodawa-Spencer gravity. As the original proposal is on Calabi-Yau threefold. And with Kevin Costello, like a couple of years ago, we developed this formulation to uptree Calabi-Yau. And also it can encode this open string as well. And we conjecture like this is going to be mirrored to this higher genus mutant variance in this holomorphic limit. So the way you couple to open string is also interesting. Like you have to couple with holomorphic consignments in the large N limit, and leading to what we call like open-closed BCV theory. And also leads to the notion of twisted supergravity, because we conjecture like this one is going to be equivalent to a twisted version of supergravity in the sense that in a particular sense. So now I want to understand how to use this model to compute some numbers, some invariance out of this theory. So I mentioned like this new formulation can be done on any kind of Calabi-Yau of any dimension. So the easiest example, simplest example is on elliptic curve. So if you try to quantize, look at quantum B model, quantum B theory on the curve, you will find like this model is given by a chiral deformation of free boson by a complicated expression. And this expression looks like this, but it's some kind of quantum corrections. And they are actually bosonic realizations of so-called W1 plus infinity algebra. So it looks complicated, but it actually has a very it's a closed formula. Then if you compute the chiral index of this model, and in the sense I just described, it becomes a Q trace on the right-hand side. On the other hand, if you can compute a model, which is this commutative invariance on the mirror elliptic curve, and they're computed by a robot digraph for the case of one descendant of the volume form. And then the full formula is obtained by Okenkopf planetary panda. Then you can check both sides, like the A sides are given by this stationary Romanov-Witten invariance. And the B side is given by this chiral index, this trace. You can check these two are the same. And how this is proved? Actually, the way you prove this one is the following. Like the work of Okenkopf planetary panda, actually they show its generating functions are given by some trace on the fermatic like BC system, fermatic system. And the left-hand side, the BCV theory actually is a chiral boson. So how these two things can be equal is a famous boson fermion correspondence. So in this example, you can see like this quantum mirror symmetry is a version of like boson fermion correspondence, and this is one application of this chiral index. But actually, as I mentioned, this is the original motivation why I started to develop this kind of chiral index story. Okay, great. So lastly, I'd like to state the main theorem today. So first one is like happy birthday, y'all. And then happy birthday, YMSC. So thank you very much.
Comments?
So there's a similar work of chiral algebra by Ballance and Greenfield. Did they have this structure of this correlation function obey holomorphic anomaly equation?
We only studied this beta gamma BC system because somehow it's related to this differential operator on the loop space. And actually, you can also do chiral boson, and you get the same results for this anomaly equation. But in general, we haven't done much yet. So, but I would expect something similar, but I don't know the answer. Questions?
Yes, if there are no questions, let's speak again.
Thank you.